In part 2 of this lecture, we'll spend our time discussing the free energy change deltaG that I promised would be a good way to predict reaction spontaneity. Let's talk about where this deltaG term comes from. In the 1800s, J. Willard Gibbs proposed a definition for something called Gibbs free energy G, which was a new state function, and he defined it simply as the sum of the enthalpy of a certain state minus the absolute temperature times the entropy of that state. This is a literal definition. Since G, H, and S are all state functions, we can put this in a more useful form. deltaG, which we simply call the change in free energy, is equal to deltaH minus T delta S. We can connect the sign of deltaG with reaction spontaneity by remembering the second law of thermodynamics, which, if you recall, said that any spontaneous reaction or process results in an increase in entropy of the universe. Delta S of the universe is greater than 0 for any spontaneous reaction. If we write out the definition of delta S of the universe, it makes sense that it's a sum of the delta S of the system plus delta S of the surroundings. I'm now going to make a substitution which seems rather arbitrary. I'm going to substitute minus delta H of the system over the absolute temperature for delta S of the surroundings. Now, I can't defend the substitution very well, but I can defend it a little bit by recalling that we discussed before that we could equate delta S of fusion, delta S of melting for ice to water, with the term delta H of fusion over absolute temperature. So I'm doing a substitution of delta S with delta H over absolute temperature. Now, in addition, I introduce this minus sign here because I'm flipping the way we're looking at this. Delta S of the surroundings, of course, is the entropy change from the viewpoint of the surroundings. I'm now flipping this around so that we're looking at it from the system's point of view, so I introduce this minus sign here. Now, if you accept my substitution, we can move on a little farther by multiplying everything through by minus T. If I do that, we get minus T delta S of the universe equals minus T delta S of the system minus T times our minus delta H of the system over T term. And of course, these T's cancel out. And so we'd have minus T delta S of the universe equals minus T delta S of the system plus delta H of the system. We can rearrange this so that our delta H of the system on the right comes first, and then we have minus T delta S of the system. What I want you to note at this point is that all the terms on the right are from the system's point of view. Well, let's compare this equation that we've derived here with our equation for deltaG, which we got from the definition of free energy introduced by J. Willard Gibbs. You'll notice here that delta H, of course, is the delta H of the system or the reaction. Delta S here is, of course, delta S of the system. So what we have here is this part of the deltaG equation is equivalent to this part of this minus T delta S of the universe equation. So we can equate deltaG with minus T delta S of the universe. Now recall again, the second law of thermodynamics states that for any spontaneous process, delta S of the universe has to be greater than 0. So if delta S of the universe has to be positive for a spontaneous process, and we've put a minus T in front of it, it means that deltaG would have to be negative for any spontaneous process. So I've rewritten our equation for deltaG here and reminded you again that the sign of deltaG will be negative for a spontaneous process, which of course means that the sign of deltaG will be positive for a non-spontaneous process. At standard conditions, each gas at 1 atmosphere of pressure, any solutions at 1 molar concentration, solids and liquids in their pure forms, and elements in their standard states at 298, we could say that the standard change in free energy equals the standard change in enthalpy minus T times the standard change in entropy. Let's calculate the standard free energy change in kilojoules per mole for the following reaction that we've looked at before. This was the decomposition of solid N2O5 to nitrogen dioxide and oxygen. And if you recall from a previous slide, we said that this reaction's been observed to be spontaneous, so we expect deltaG to be negative. deltaH was a positive 220 kilojoules, and deltaS was a positive 810.8 joules per K. If we're going to add an enthalpy term to an entropy term, we are going to have to deal with reconciliation of units. So I'm going to change the joules to kilojoules in this deltaS term. So I'm going to convert 810.8 joules per K to 0.8108 kilojoules per K. Now we'll simply calculate deltaG, the standard free energy change here, using this equation. I substitute in 220 kilojoules for deltaH and put in the temperature specified, 298, put in deltaS in kilojoules per K, the units of K cancel out, and we get minus 22 kilojoules. Recall that the enthalpy term here does not favor spontaneity. The deltaS term does favor spontaneity because it's positive, but I want to look at this from a little different angle. And I want you to note that the minus T deltaS term here comes out negative because of the fact that deltaS is positive. And you say, well, so what? Well, it just gives us a little quicker way of looking at the effect of entropy and enthalpy. So since the deltaS term is positive, the minus T deltaS term comes out negative. And since this negative is of larger magnitude than this positive, then deltaG comes out negative. It's just another way of showing that it's the entropy term that makes this reaction spontaneous. Well, one of the things that you might have just noticed is that I asked us to calculate deltaG in kilojoules per mole, and you notice that our answer just came out in kilojoules. It's possible that you will see deltaG for this and other reactions being reported or being asked to be reported in units of kilojoules per mole, as I did ask here, even though it seems undeniable that there's no per mole unit in this equation. So you might ask, where did that come from? Now it may sound strange. The per mole, if added, typically refers to per mole of the balanced reaction as written. So therefore, we would understand a deltaG here of minus 22 kilojoules per mole, meaning per mole of the balanced reaction as written, which for this particular reaction would also mean per 2 moles of N2O5 consumed, or per 4 moles of NO2 produced, or per mole of oxygen produced. Now, in a similar way, we can calculate deltaG values for the other 3 examples that we've been talking about at 298 K. We're going to build an expanded table below, and I want you to note that we've introduced per mole into the units. So here are our 3 reactions and 1 melting process. For the hydrogen-oxygen reaction, recall that the deltaH was large and negative, so this is a very exothermic reaction. deltaS was negative because we're creating order, so that's unfavorable toward spontaneity. We can pick that unfavorableness toward spontaneity up in the minus T delta S term. If we take 298K times delta S, and of course first change joules to kilojoules, we get a minus T delta S term of 97.2. So recall delta G is delta H minus T delta S. We can think of this as delta G being the sum of the delta H and the minus T delta S term. In any event, you can see that delta G is just the difference between the delta H and the minus T delta S term. Delta H is pushing for negative delta G. The minus T delta S term is pushing for a positive delta G. The delta H term wins out here. Delta G is negative. You predict the reaction to be spontaneous, and of course it is. And then we say, of course, it's an enthalpy-driven reaction. Well, how about the reaction of nitrogen and oxygen to form NO2? The delta H there is positive. It's an endothermic reaction. Delta S is negative. You're producing order. Both of these are working against you with regards to spontaneity. Since delta S is negative, the minus T delta S term is positive. So when we add these two together, the delta H and the minus T delta S term, we get, since these are both positive, you get a positive delta G. We predict this to not be spontaneous, and it is not spontaneous. Both the delta H term and the minus T delta S term are positive, so of course delta G will come out to be positive. For ice melting to water, we know it's an endothermic process because if it takes place in your hand gets very cold. We know that disorder is created, so therefore the minus T delta S term turns out to be negative since the delta S term is positive. And so it appears here that the minus T delta S term is going to make delta G negative, and it does, slightly negative. So we predict that ice melting to water at room temperature is spontaneous. We know that is. And again, we say, or not again, I should say here, it's an entropy-driven process. The delta S term is positive, and the minus T delta S term is negative. Finally, for the decomposition of N2O5 to NO2 and oxygen, we did this on the previous slide. Delta H is positive, delta S is very positive, which means the minus T delta S term is very negative. So the minus T delta S term wins the day here in determining delta G. So delta G comes out to be negative. We predict this reaction to be spontaneous, and it is. And we say here it's also an entropy-driven reaction. So you want to note here that the reactions with calculated delta G values that are negative, these 3 here, are in fact observed to be spontaneous, and the reaction with the calculated delta G value that's positive, this one here, predicted to be non-spontaneous, is in fact observed to be non-spontaneous. So let's summarize these 3 reactions in one process again. Hydrogen and oxygen reacting to form water. Delta G is negative because the large negative deltaH dominates over the positive minus T delta S term. Nitrogen and oxygen forming NO2. deltaG is positive because both the deltaH and the minus T delta S terms are positive. Ice melting to water. deltaG is negative here because the negative minus delta S term, although not a large negative number, does dominate over the only slightly positive deltaH term. And for the decomposition of N2O5, deltaG is negative because the large negative minus T delta S term dominates over the positive deltaH. It is possible to estimate values for deltaG for a reaction by using what are known as standard molar free energy of formation values. So what I'm telling you here is that it's possible to get a deltaG value without using the deltaH minus T delta S equation if you have a table of what's called standard molar free energy of formation values. Those values are typically found right along with the deltaH of formation and the standard molar entropy values in tables of thermodynamic properties in general chemistry textbooks, and the table in the textbook associated with this particular course has the free energy of formation values listed. So we can calculate a deltaG using these deltaG of formation values in a way that looks very familiar, because we calculated deltaH values using deltaH of formation values. So we just take the sum of the free energy of formation of the products and subtract the sum of the free energy of formations of the reactants, and we need to keep track, of course, of how many moles of products and reactants that we're dealing with. Now, as with heats of formation values, the free energy of formation value for any element in its standard state is 0. Now, we previously determined deltaG to be 103.6 kilojoules per mole at 298 K for the reaction of nitrogen and oxygen to form nitrogen dioxide. Remember, deltaG is positive here, and this is predicted to be not a spontaneous reaction. Now, we found that deltaG by using the equation deltaG equals deltaH minus T delta S, and we had values for deltaH and delta S, and of course the temperature. What we want to do here is calculate deltaG using free energy of formation values, and then compare the result to the result 103.6 that we got using deltaG equals deltaH minus T delta S. Now, I put a table here on the right, which with just the standard molar free energies of formation values that we need. Of course, if you had a larger table, you'd have to get these values from the larger table. So in this case, deltaG can be calculated by adding up the standard molar free energies of formation of the products. Remember, the products here are NO2, and there's 2 moles of NO2. And then we subtract the sum of the deltaG of formations of the reactants, which are here both elements, so they're equal to 0. You might wonder why I left out the phase symbols for all of these. I don't have NO2 gas. I don't have nitrogen or oxygen listed as a gas. I've told you before, you need to be careful about this. And I simply ran out of room here, so that's why they're not there. So if we do the math, we get a deltaG of 103.68 kilojoules. You'll notice that the moles cancel out here, but it's understood that this is deltaG of 103.68 per mole of reaction as written. This turns out to be an excellent agreement with the value of 103.6 that we got by using deltaG equals deltaG equals deltaH minus T delta S, which is great. So you might think, well, this might be an easier way to get a deltaG value than going through the deltaH minus T delta S equation. You want to keep in mind here, though, that the values of deltaG obtained by the two different methods don't always agree so closely. So I would look at getting deltaG using this method as more of an estimate, and getting deltaG using deltaH minus T delta S as a more exact way to get a deltaG. Again, you might say, well, these two came out close. Well, let's do another example. If you actually did a comparison using the reaction of N2O5 going to NO2 and oxygen, the value we got using the value we would get using this equation here is minus 60.6, which still does predict that the reaction's spontaneous, which is good because it's negative, but it's not very close to the value of minus 22 obtained by using the equation deltaG equals deltaH minus T delta S. So in this case, it's suspected that there's probably some uncertainty in the data used for N2O5 solid. If we go back to our original equation for calculating deltaG, you can see that deltaG has an obvious temperature dependence built in. However, you want to keep in mind that the effects of changing temperature on deltaG depends on the signs of deltaH and delta S. Let me show you what I mean. Let's look at 4 cases of different combinations of signs for deltaH and delta S, and let's see how that turns out to affect how temperature affects deltaG. So for example, let's suppose in case 1 we have a negative deltaH and a positive delta S. Well, that means the minus T delta S term will be negative, and that means that no matter what the temperature is, deltaG will come out negative. Well, again, why is that? A couple different ways we can look at it. Let's look up at this equation. If deltaH is negative, that's great. If delta S is positive, that means that no matter how low or how high this temperature is, this whole term, minus T delta S, is going to come out negative. And so no matter what the temperature is, deltaG is going to come out negative. So we'd say if you have a reaction where the deltaH is negative and the delta S is positive, that reaction is going to be spontaneous at all temperatures. How about if we look at a different case where deltaH is negative, but delta S is negative also, which means that the minus T delta S term would be positive. Well, here, deltaG could be negative at lower temperatures. So again, deltaH is negative, the minus T delta S term is positive, so what you want is T to be as low as possible. So at lower temperatures, it's possible that the minus T delta S term will not be positive enough to overcome the negative deltaH. So the reaction will be spontaneous at lower temperatures. deltaG will be negative. If you raise the temperature, it would raise the influence of this minus T delta S term, and you get to the point where it overwhelms the negative deltaH term. deltaG then becomes positive, and so we say the reaction, which is spontaneous at the lower temperatures, becomes non-spontaneous at the higher temperatures. That almost seems counterintuitive, but it's hard to argue with the math. How about for case 3, if we decided deltaH was positive and delta S was positive, that means the minus T delta S term would be negative. Well, delta H term argues for non-spontaneity. The minus T delta S term argues for spontaneity. So the minus T delta S term is not going to win out if temperature is low. So at low temperatures, the reaction could be non-spontaneous. Delta G would be positive. But if T gets large enough, the effect of this minus T delta S term becomes more influential, and so delta G could become negative at the higher temperature. So we say in this case, case 3, the reaction would be non-spontaneous at lower temperatures, but it would become spontaneous at higher temperatures. Now, if your reaction is unlucky enough to be in the category, well, delta H is positive, delta S is negative, which means the minus T delta S term is positive, it doesn't matter what the temperature is, that reaction or process is going to have a positive delta G, and it's just not going to be spontaneous. Let's look at a reaction that we looked at before, and we looked at it in terms of the Le Chatelier's principle, and that was the Haber process, which involved the production of ammonia through the reaction of nitrogen plus hydrogen producing ammonia. And we said this is an exothermic reaction. Delta H is minus 92.4. Delta S was minus 98, which makes sense because you're creating order. We can calculate a delta G for this reaction at 298 K. Well, recall here, this reaction appears to come under case 2 because delta H is negative, delta S is negative, so delta G should be negative at lower temperatures and positive at higher temperatures. Well, let's calculate what it is at 298 K. At 298 K, it's minus 33 kilojoules per mole, and so it is spontaneous at 298 K. Of course, to do this reaction, this calculation, we converted joules to kilojoules in the delta S term. So the reaction as written is spontaneous at 298 K. Well, with delta H being negative and delta S being negative, as I mentioned before, this reaction fits case 2 from this table. Therefore, we would predict that raising the temperature should result in a less spontaneous reaction or even a non-spontaneous reaction. So let's raise the temperature and see what happens to delta G. Case 2 predicts that delta G should become progressively less negative and then go positive if we raise the temperature far enough. So on the next slide, we'll do that. So here, let's calculate delta G at 420 K. So we've raised the temperature from 298 to 420. One of the things you have to assume here is that the delta H and delta S terms do not change significantly over the temperature range that we're trying to compare. So what we hope is that delta H and delta S are not drastically different at 420 K compared to what they are at 298. Well, for about 100 Kelvin change, delta H usually changes by less than 1% and delta S by 2 to 3%. So therefore, we just use the standard enthalpy changes and standard entropy changes in this calculation. So if we calculate delta G at the new temperature of 420 K, we get minus 9.1 kilojoules per mole. Well, the reaction as written here is still spontaneous at 420 K, but it's less spontaneous at 420 K than it was at 298. Delta G is less negative. That's what we would predict because this is a case 2 scenario. Now recall in a previous module discussing the concept of equilibrium, we discovered that the equilibrium constant K for this reaction decreased as temperature increased. So let's say that again. The equilibrium constant K decreased as the temperature increased. That would mean as the temperature increases, there's less tendency to go to products, which is consistent with the thought that at the higher temperature, the reaction is less spontaneous, less interested in going to products. So a little later on, we'll discuss the connection between deltaG and the equilibrium constant. So it appears that as the temperature is raised, that this reaction becomes less spontaneous, but that begs the question, at what temperature does it become non-spontaneous? What we need to do is just calculate what temperature we need to go over the crossing point between spontaneity and non-spontaneity, because again, this is a case 2 scenario, which means if we raise the temperature high enough, the reaction will become non-spontaneous. So what we're going to do is we're going to calculate the temperature at which deltaG goes to 0. Remember, it was minus 33 at 298. We raised the temperature to 420, it's less negative, it's minus 9.1. So we're asking what temperature would we need to get deltaG equal to 0, which would be the crossing point from a negative deltaG to a positive deltaG. If we say deltaG equals deltaH minus T delta S, and that has to equal 0, then we can say, well, that means that deltaH equals T delta S. And T would be deltaH divided by delta S. Again, we're using the values of the standard deltaH and standard delta S, and we've converted the units for delta S into kilojoules. We get 466 Kelvin. If you want to see how the units work out here, you'd have kilojoules per mole over kilojoules per mole per K, which is equal to kilojoules per mole times moles times K over kilojoules. And of course, kilojoules and moles cancel out, and you're left with units of K. Well, what we conclude is that we would estimate that the reaction for the production of ammonia from nitrogen and hydrogen is non-spontaneous above 466 Kelvin, because we've just calculated, or at least estimated, that the temperature at which deltaG would go to 0 is 466. So any temperature higher than that would make deltaG positive, or would make this reaction non-spontaneous.